learn math with Jeremy. Je m'appelle Jeremy et vous, comment t'appelez-tu? Je parlais en français, d'accord. Écoutez attentivement. Okay, I'm just joking. I'm actually teaching you in English today that En is a sequence of measurable subsets of Rd such that the measure of any two of those sets is equal to 0 if they are not the same. We want to show that the measure of the union is actually equal to the summation of the individual measure of the set. So when you see this type of problem, the first thing to do is just so you want to do some work, and you have to take off your jacket first because you want to do some real work now. If we assume that the En are disjoint, then there is almost nothing to prove again. But then, obviously, if they are disjoint, by countable additivity. If you don't know about countable additivity, I have given the proof of countable additivity before in my former video. I'm gonna leave the link in my description so you can check them out. So, but let's get started. So, for us to work with this, the first thing is that we need to make sure we have the measurable sets we have are disjoint. So we're gonna construct one now. So proof. What is the first thing? I will say let F1 be equal to E1, then Fn to be equal to En minus remove union of k starting from 1 to n minus 1 of ek or ek. What does this ensure? This ensures that my Fn are disjoint. So that is the first thing you need to know. The Fn's are disjoint. Not only are they disjoint, they are measurable, obviously. And notice that the union from k starting from 1 to infinity of the Fk is exactly the same as the union of k starting from 1 to infinity of Ek. Now, how do I know they are disjoint? Let me just give you, if you can't see this yet, if you can't see why they are disjoint yet, I'll give you a quick example. Let's say E1, for example, is 1, 2. Let's say E2 is 1, 2, 3, and let's say E3 is 1, 2, 3, 4. Obviously, these three sets are not disjoint, but according to this construction, look at this. According to this construction, what can you see? That means, according to this construction, F1 is E1, that is 1, 2. F2 will be equal to what? F2 will be equal to E2 minus E1. Since minus E1, what is E2 minus E1? E2 minus E1 just means subtract every element in E1, then you are left with what you have in E2. So you just have only 3 here. Then F3 will be E3 minus E1 and E2. So this is E3. Subtract E1 and E2, you are just left with only 4. So basically, what does this say? You can see that F1 and F2 are disjoint, F1 and F3 are disjoint, F1, F2, F3, they are all disjoint. There is no common element between them. Their intersection is empty. And if you take the union of say k starting from 1 to 3 of Fk, that is union of F1, F2, and F3, you will see that will exactly be the same as the union of k starting from 1 to 3 of Ek. That is what this is saying. Now, that is why the FNs are disjoint. The reason why we construct this set first is so that we make them disjoint. And we have to make them disjoint in such a way that by the time we take the union of everything, we recover what we're looking for. We recover the union of the EMs. We've discussed before that if you have a complement of a measurable set is measurable, as well as union and intersection of measurable set is measurable. That is why the FNs is measurable. And this one as well, as you can see with this illustration I've given to you, they are the same. So what does that mean? The measure of the union of k starting from 1 to infinity of ek will exactly be equal to the measure of the union of k starting from 1 to infinity of fk, and this is by countable additivity. By countable additivity, since all the fk are disjoint, this will be equal to summation of k starting from 1 to infinity. I'm going to drop a link in my description for you to see what we call countable additivity. Like what I have explained before, this union will come out, then you have summation, k starting from 1 to infinity. When it comes out, so when this union come out, it becomes summation, then you have measure of fk. So that is what we have. We are almost close to this. We just need to prove that the outer measure, like the measure of fk, is equal to measure of ek. If we can prove that the measure of fk is equal to the measure of ek, then we are done with the proof, because we just need to show measure of the union is equal to summation, then measure of ei. And this is measure of ei or ek is still the same. Then if I can say this is equal to measure of ek, of course I've already showed that it's equal to measure of fk, but I need to show that measure of fk is equal to measure of ek. So that is what we are left to do now. I need to prove that the measure of fk is equal to measure of ek. That is the aim, that is the goal of what we need to do right now. And to do this, we just need to prove that this is less than equal and this is greater than or equal. This is a very important tool in mathematics generally and in measure theory especially. So this is what we need to do. So now, from what we have constructed here, if we look at what we have constructed here, Fn, we said we know Fn is equal to En, removing the union of k starting from 1 to n minus 1 ek. So how does this help us? Now, if I want to write it properly, this is Fn to be equal to En. This means intersection union of k starting from 1 to n minus 1 of ek complement. I hope you are aware of this. This thing means minus this, minus all this thing here. So, and if you want to write, another way to write this is just saying this exactly means intersection of union of k starting from 1 to n minus 1 ek, then complement. That is what you have. Now, when you have intersection of two sets, it will obviously be inside one of them. It will obviously be inside one of them, right? Because say for instance, if you have done E1 intersection E2, let's say for instance you are doing E1 intersection E2. E1 intersection E2 is basically 1, 2. You see, 1, 2 is fully contained in E1. 1, 2 is fully contained in E2. So when you take the intersection of two or more sets, you are very sure that it will be inside, like it will be fully contained in one of them or any of those sets you take the intersection. So that is what we have there. And now we need to, so by monotonicity of the outer measure, it means that the measure of Fn, or the outer measure of Fn, is less or equal to, that is the meaning of monotonicity. Fn is inside En. By monotonicity, it means that the measure of Fn is less or equal to the measure of En. That is what we have. So I have proved, that means that I have proved this side of the equation. Then I am left with this inequality. I've proved this inequality, then I'm left with this other inequality. So now, since union of k starting from 1 to n minus 1 of ek are measurable. Of course, we've proved this before, that union of a measurable set, in fact, countable union of a measurable set is measurable. I will leave all this link to you in case this is your first video you're watching with me. But since the union of k starting from 1 to n minus 1 of ek are measurable, what does that mean? By the Countable condition, Countable condition says that the outer measure of t must be equal to outer measure of t intersection e plus outer measure of t intersection e complement. That is what the Countable condition say. That is, when you take for any t in your domain in Rd. So since we are in Rd, for any t in the domain, when it's a set immeasurable with respect to the Countable condition, it has to satisfy this property. We've said this before as well. So now, I'm gonna make my t to be En. That is what I will do. And because this is measurable, it means that it has to be equal to the outer measure of En intersection u, k starting from 1 to n minus 1 of ek, plus the outer measure of t here is En intersection u, k starting from 1 to n minus 1 of ek complement. That is what you will have, because by definition of the outer measure, Countable condition. So now, this is the outer measure of En. Now, what can we say about this? Really, we can't say too much about this, but we know this is equal to the outer measure of. I can bring out this union to have this big union, k starting from 1 to n minus 1, then so that I have En intersection ek. That is the first one I have here, plus outer measure. In this case, what do you notice here? En intersection union of k starting from 1 to n minus 1 of ek all complement. That is exactly En intersection union of k starting from 1 to n minus 1 ek all complement. That is Fn. That's how we define our Fn. En intersection the union of this complement, the intersection of that complement. So now this is exactly Fn. That is what we have. Now, to round off this, the outer measure of En by countable subadditivity, by the property of the outer measure, by countable subadditivity, this will make it less or equal. By the time this union come out, it becomes less or equal. Summation, by the time this union come out, it becomes k starting from 1 to n minus 1 En intersection ek. That is what you have. This is just the property of the outer measure plus Fn. That is what we have. But from the condition we are given in the question, remember, this is happening. The outer measure of EI intersection EJ will always be 0, provided what they are different. Provided these two elements are different. So now, can you really see that these two are different? Because this is k starts from 1 and it stops at n minus 1. So this one can be 1, 2, 3 till it gets to what? N minus 1. It can never get to n. So that means they will always be different. Each of these summation it should be En intersection E1, En intersection E2, till you get to En intersection En minus 1. They can never be the same. So that means the measure of this is 0, and it will make all of this to become 0. So this will be 0 plus outer measure of Fn. And what have I done? This is what I have proved. I have proved that the outer measure of En is less or equal to, outer measure of En is less or equal to outer measure of the Fn. And we are done. So this is the other one we have proved. Outer measure of En or Ek is less or equal to outer measure of Fn. So by so doing, by combining these two stuff together, like where is the first one? This one. I have proved this. I have proved this. What does that mean? It only means that outer measure of En is same as the outer measure of Fn, and the proof is complete. So we have outer measure of the union of k starting from 1 to infinity of Ek to be equal to summation of k starting from 1 to infinity. No, I've said it's equal to, this already is equal to outer measure, summation of outer measure of Fk. But I already proved that outer measure of Fk is same as outer measure of Ek, so this is same as. And the proof is complete. So when you're done now, you need to dust yourself, you know. Wave goodbye to measure theory. Au revoir, monsieur, au revoir, madame, au revoir, mademoiselle. À bientôt. Bisous, bisous. See, the day is gone. It's gone. Quel confetti aujourd'hui? Il fait beau.